All right. This is Chapter 11, Intro, 4th edition, Advanced Chemical Bonding Models. In Chapter 10, we talk about ionic bonds and covalent bonds. And that's fine, and they explain a lot of what we see, because in chemistry we don't want to know just the what, but the why. We want a good explanation for all our observations, not just some of them. Anyway, we covered ionic and covalent bonding in Chapter 10, and that was fun. Now we're going into Chapter 11 with advanced bonding theories, because ionic and covalent bonding don't explain everything, and we want to be able to explain everything. Like, why do we break the octet rule? We talked about it in Chapter 10. We gave you the what, but we didn't give you the why. Or how does that even happen? Or what are the theories behind breaking the octet rule? Well, that's what we're going to get in Chapter 11. Okay. So when we draw a Lewis structure, like what we did in Chapter 10, it shows you the connections of the atoms in the molecule, but they don't give you the shape, because molecules exist in 3 dimensions. But we do use Lewis structures to help us to determine shapes. So what does determine the shape of a molecule? Well, the idea here is bonds and lone pair electrons are all negatively charged, so they all repel each other. So the idea here is the electrons and all the different bonds in your molecule, the bonds will repel each other. The lone pairs will repel each other. The lone pairs will repel the bonds, because they're all negatively charged. They're all packed with electrons. And so the idea here is the shape is determined by those electrons wanting to be as far apart as possible. This is called the valence shell electron pair repulsion model, VSEPR for short. So to be able to do shapes with VSEPR theory, we need to be able to count electron groups, also known as VSEPR groups. Electron groups are regions where we find electrons in our molecule. Now, the potentially confusing part of this is a double bond counts as one electron group, because it's one location where you find electrons. So in my example here, my hypothetical molecule here, my central atom, A, has 4 electron groups. Each single bond is an electron group. So here's an electron group here, electron group here. This double bond is 1 electron group. This lone pair is 1 electron group. So this A, hypothetical A, is surrounded by 4 electron groups. 1, 2, 3, 4. Okay, so now that we can count groups, let's move on. Now the way to visualize how the electrons repel each other in the bonds and the lone pairs is imagine that they're balloons. If you had 2 balloons stuck together, they'd want to be as far apart as possible, and they'd have this linear arrangement. If you have 3 balloons, it would look like this. If you had 4 balloons stuck together, they would look like that. So this is a way to visualize these different shapes that are generated by these electrons wanting to be as far away as possible. So imagine an electron group is represented by 1 balloon. And this is how far apart these guys can get from each other. Okay? So we're going to walk through how many electron groups you can have around your central atom and what shapes you get. So you need to be able to count the total number of lone pairs of electrons that are not being shared. And you have to be able to count single, double, and triple bonds. And all we care about is the central atom. We don't care about what's going on with the outermost atoms. All we care about is the electron groups on our central atom. Okay? So, starting at the top, if we have 2 electron groups around the central atom, we have a linear molecule, and our bond angle is 180 degrees. That means the farthest apart these 2 bonds can get is 180 degrees. And if they can get that far apart, they will. Okay? If we have 3 electron groups, we have a trigonal planar geometry that looks like this. Our bond angle is 120 degrees. The bond angle means the angle between the bonds around the central atom. Okay, so this guy right here, this is trigonal planar. And it's called trigonal planar because there's 3, and they all lie in a plane. So they would lie flat in the palm of your hand or flat on a tabletop. If you have 4 electron groups around your central atom, you have a tetrahedral arrangement. And your bond angle is 109.5. And yes, you do need to know your predicted bond angles. It's part of the package. If you have 5 electron groups around your central atom, now we're breaking the octet rule. Okay? If we have 5 electron groups, we have a trigonal bipyramidal geometry. So these are all my electron group geometries. Okay, linear, trigonal planar, tetrahedral, trigonal bipyramidal. Here are my bond angles. We'll go into that more later. And if you have 6 electron groups around your central atom, the electron groups will take on the geometry of an octahedral. And you could see the example problem in a separate lecture, 11.1. Those bond angles are 90 degrees. All right, so now that we have the electron domain geometry, the electron group geometry, now we need to figure out the molecular geometry, which is different. The electron group geometry accounts for everything, all the bonds and all the lone pairs. Your molecular geometry ignores the lone pairs and just looks at the geometry of the bonds. Okay, we're going to walk through all of these. Okay, so if we have 2 electron groups around our central atom, we have a linear molecule. And they will form a line. That's why it's called linear. An example here is carbon dioxide. There are 2 electron groups around my central atom, 1, 2. To get as far apart as possible, they want to be 180 degrees. And in fact, this is observed for carbon dioxide. Again, we only care about what's around the central atom. We don't care about what's going on with the oxygens right now. Okay? If you want to see a 3D visualization of linear, there's a YouTube link you can watch. Okay? If you have 3 electron groups around your central atom, there are 2 molecular geometries. If all your electron groups are bonds, you're trigonal planar. So in every case, if all your electron groups are bonds, the molecular geometry and electron group geometry are the same. So if you have all bonds for all 3 electron groups, you have trigonal planar molecule, like SO3 right here. Yes, we're breaking the octet rule here too. That's because of our formal charge lesson we did the other day. Okay, but what if we have 3 electron groups, but 2 are bonds and 1 is a lone pair? That's called bent or angular, because we're only looking at these guys. We're only looking at the bonds to determine the shape. Now the lone pair electrons influences the shape, but he's not part of the name. This is bent or angular. These lone pairs are repelling the bonds and pushing them away, so it's not linear. This is bent or angular. Again, there's YouTube videos if you want to see 3D visualizations of these guys. If you have 4 electron groups around your central atom, you have 3 possible molecular geometries. If all your electron groups are bonds, you're tetrahedral. There's a video for that. If you have 1 lone pair and 3 bonds, you're trigonal pyramidal. And there's a link for that if you want to take a look at that in 3D animation. If you have bent angular, that means you have 2 bonds and 2 lone pair. There's examples of these on the next slide. Okay, so here's my tetrahedral. I have all bonds for methane. Here's my trigonal pyramidal for ammonia. I got 3 bonds and a lone pair. So here's my trigonal pyramidal right there. And here's my bent or angular for water. Got 2 bonds and 2 lone pair. Now what's going on here with this slide is that these lone pair electrons have greater repulsions than the bonds. So they will compress the bond angles. They're going to push the bonds away from the lone pair because they occupy more space. So that's what I've got going on the right over here. This is the space taken up by a bond. Here's a space taken up by a non-bonding pair. You see this is a lot bigger. So these lone pairs are pushing the bonds away from them and compressing those bond angles. So in a regular tetrahedral, you have 109.5 when all your electron groups are bonds. If you have 1 lone pair, you're going to compress the bond angles to 107. If you have 2 lone pair, you're going to compress again even more to 104.5. You do not need to memorize the compressed bond angles. You only need to memorize the 109.5 because that's your idealized bond angle. Okay, onward we go. Now double bonds and triple bonds are also have more repulsion than single bonds. So they act a similar way as the lone pair. They're going to push away those single bonds and compress that angle. So since this is trigonal planar, but I don't have 120 degrees, the double bond is compressing this angle and making it 111.4 instead of 120 and pushing away those carbon-chlorine bonds. So you have bigger bond angles here, and then a smaller one for your chlorine-carbon-chlorine bond angle. Because you got 4 electrons here and only 2 here and 2 here, so they're more repulsive and they're going to push away those bonds with more force. Okay, so there's that. Again, you don't need to memorize these special cases, just the ideal bond angles, the 109.5, the 120, and the 180. Okay, onward. So we have more shapes for when we break the octet rule. If we have 5 electron groups, we have trigonal bipyramidal. And 6 electron groups, we have octahedral. But we have additional shapes that are possible if some of our electron groups are a lone pair. So this is when you have all bonds. Okay, I've got 5 electron groups around my central atom. There are 2 distinct positions with this geometry. You've got the equatorial position, where you've got these 3 in one plane here with the 120-degree bond angles. Then you have the axial position, where these 3 are in a line. Okay, they're different types of positions. These form a line, and these 3 here form a triangle. This is called the equatorial positions. These are the axial. Okay. If we have lone pair electrons as one of the electron groups, they're going to take an equatorial position, and that will influence the shape. So, if you have no lone pairs, your molecular geometry and electron group geometry are the same, trigonal bipyramidal. If you have 1 lone pair electron and all the other ones are bonds, you have a seesaw shape, which is right here. If you imagine tipping this back and forth, it would act like a seesaw. If you have 2 lone pairs and 3 bonds, this is called T-shaped because it looks like a T. Doing. Sorry. Anyway, if you want to see a YouTube video from Tyler DeWitt, he has some nice toys that help illustrate in 3 dimensions what these different shapes look like. I've got a link here for 5 electron groups. The next slide has the link for 6 electron groups. Okay, so if you have an octahedral domain and you have 6 electron groups, all positions are equivalent. And we have 3 possible molecular geometries. Octahedral, if all your electron groups are bonds. Square pyramidal, if you have 1 lone pair, and that's this guy over here. And you imagine there's a lone pair down there. Okay, and then you have square planar where you have 2 lone pair and 4 bonds. This is 1 lone pair and 5 bonds, 2 lone pair and 4 bonds. And this is what that looks like, square planar. Again, there's a YouTube video. Tyler DeWitt has very good videos. He's got a nice little set of toys to help you visualize these different shapes. Again, examples 11.2 and 11.3 are done in a separate video. Okay, if you want to look at the shapes of larger molecules, in this type of case, you're going to have more than 1 central atom. So you look at each central atom one at a time and determine the geometry around each one. Again, 11.4, a different video. Okay. So why are we doing this? Well, we're doing this because molecular shape will influence molecular polarity. And molecular polarity has big-time real-world consequences. If you have a polar molecule, it will impact its boiling point, melting point, chemical behavior, will it dissolve in water or not, has large impacts. So shape determines, is your molecule as a whole polar or not? Because you can have polar bonds, but that doesn't mean you have a polar molecule. You've got to look, do I have polar bonds? And you also have to look at the geometry of the molecule. That's why these shapes are important. They determine, do you have a polar molecule or not? And we'll go through how this works. Okay, so the thing we need to know to start is if we have a polar bond, and we have this permanent separation of charge, and from there we get a dipole moment. These dipole moments are vector quantities. That means they have magnitude and direction. So if you've got a symmetrical molecule and your dipoles are pointing in opposite directions, they cancel out. And when that happens, your molecule is nonpolar. Here's an example. CO2. He has polar bonds. These carbon-oxygen bonds are polar bonds, but they're pointing in opposite directions, so they cancel out. This is a nonpolar molecule. So since CO2 is symmetrical, He's nonpolar. Imagine this is two children pulling on a string. If they each pull on it with equal force, the string doesn't move. Nonpolar. Here's another example. BF3, boron and trifluoride. Polar bonds, but trigonoplanar is a perfectly symmetrical shape. So if I have 3 children pulling on a string with equal force, it doesn't move. Nonpolar. These 3 bonds cancel out because this is perfectly symmetrical. Okay, so here's an example where we're asymmetrical. We don't have symmetry. Germanium dichloride. Imagine one child let go of the string. Now we have a magnitude and a direction for the overall dipole moment of the molecule. Put differently, this molecule here is not symmetrical. To be symmetrical, I have to be able to cut it in any direction and it'll look the same on both sides. So if I cut it on this direction here, I've got 2 chlorines on one side and a lone pair on the other. It is not symmetrical. This is a polar molecule. So the shape helps determine symmetry. If you are symmetric, you're not polar. If you're asymmetrical, you are polar. Another example is water. This is not a symmetrical shape. If I cut a line, draw a line this way, they look different on either side of the line. I got hydrogens over here and lone pairs over here. I have an overall dipole moment with my negative charge on the oxygen end, the positive charge on the hydrogen end. This is a polar molecule. He is not symmetrical. If I cut him in a line vertically, yes, he's symmetrical. But if I cut it horizontally, he is not vertical. If I cut it horizontally, it is not symmetrical. And to have symmetry, I have to be able to cut it in any direction, and it'll be the same on both sides. Okay, water is polar because it is not symmetrical. All right, onward. So if you want to figure out if your molecule is polar or not, you have to ask yourself a series of questions. Question 1, is it covalent or ionic? Well, if you're ionic, polarity has nothing to do with it, and you can move on. But if you're covalent, you have to ask yourself more questions. Are the bonds polar? Look at the difference in electronegativity. That will tell you if the bonds are polar. If the answer is no, the molecule as a whole is nonpolar. So in any hydrocarbon, with like fats and oils, all those carbon-hydrogen bonds are nonpolar bonds. So all your fats and oils and whatnot, and gasoline and stuff that all have carbon-hydrogen bonds, they're nonpolar. So they don't dissolve in water because water is polar. Okay, so if the bonds are not polar, you have a nonpolar molecule. If the bonds are polar, you have to look at the shape. Is it symmetrical? If your molecule is symmetrical, you're nonpolar. If you're not symmetrical, you're polar. Because if you're not symmetrical, you have an uneven distribution of charge in your molecule. The thing to remember when you look at the shape, if you have different atoms attached to your central atom, they will have different bond polarities, and they can give you a polar bond if they're different. Okay, so you got to look at also what's attached. Again, 11.5 in the book is in a separate video. Okay, so that's it for molecular shape. We're going to move on now to different bonding theories to help us explain how did we get 5 or 6 electron groups around our central atom? Why did we break the octet rule? How did that work? And why is that still stable? Why is that okay? Well, we're going to go into that. Valence bond theory and hybrid theory and hybrid orbital theory we will cover in this lecture. Molecular orbital theory will wait until after our 3rd exam. So we'll go into that next week. Because when we make all our observations in the natural world, we want to look to the natural world for explanations. We don't want to do any magical thinking. So we need to come up with some ideas of, why am I seeing this? Why is this compound stable even though he breaks the octet rule? We're going to go into this. So the first thing we need to talk about is valence bond theory. The idea here is that when you have 2 atoms coming together to make a molecule, like in my example here, I have 2 hydrogens coming together to make H2. These 1s orbitals overlap. And where they overlap, that's shared space. There's your bond. Okay? Now, another example here is hydrogen chloride. Your electron for hydrogen is in a 1s orbital. Your valence electron in chlorine is in a 3p orbital. You get this orbital's overlap, there's your bond. Last example, chlorine-chlorine bond, 4 molecular chlorine. That valence electron is in the 3p orbital, so you get that orbital overlap, there's your bond. That shared space is your bond. You have to keep in mind, if these two atoms that want to make a molecule, if they're too far apart, there's no shared space, no molecule. If they get closer together, that's good. Even closer together, even better. I've got a lot of overlap, I've got a lot of sharing, I'm happy. But if I get too close, the nuclei and the atoms start repelling each other. And then that's no good. So your distance between your atoms and your molecule is determined by the attraction of the electrons to the other nucleus and the repulsions of the nuclei repelling each other, because the nuclei, remember, are both positively charged. So they want to get close, but they can't get too close. And that determines the length of your bond. Okay, so next we're going to put together two ideas. Vesper theory, how these bonds want to be as far apart as possible, and the shapes of these orbitals. How do we put these two guys together? We're going to put these two ideas together and come up with your hybrid orbitals. Hybrid orbitals are when you mix atomic orbitals to form a new hybrid orbital. Think of it as like knocking down walls in a house to make a new room. And the room will have a new shape that will give a shared space so a pair of electrons can hang out together and make a bond. So hybrid orbitals are formed by mixing atomic orbitals to make new orbitals of equal energy. If we have orbitals of equal energy, they're called degenerate orbitals. And you don't gain additional orbitals. You'll have the same number of orbitals you started with, they just have a new shape. So if I mix two orbitals, I'll create two hybrid orbitals. If I mix 3 orbitals, I get 3 hybrid orbitals. Okay, the total number of orbitals stays the same. Okay, so let's look at an example here. Here's beryllium. This gives us our explanation of why beryllium does not follow the octet rule. Okay, so what's going on here is beryllium starts out like this. He has 4 electrons, he'll stick 2 in 1s and 2 in 2s. But if he wants to make a compound, what is he going to do? He's going to promote one of those s electrons to p, then he's going to hybridize these guys. And his hybrid orbitals are called sp, because they have elements of s and elements of p in their shape. So now I've got 2 unpaired electrons. They're both available for business. They're open for business, and they can each make a bond. So we get compounds like beryllium difluoride. This breaks the octet rule. Why? Because of these hybrid orbitals that beryllium made. So he can make 2 bonds. And he's perfectly happy like this. This is fine. These 2 empty p orbitals, we're not using them. We're going to leave those guys alone. We only care about these sp hybrids. Okay? Now if we have sp orbitals, what do they look like? We're going to mix 1s and 1p, and they're going to look like this. They'll have elements of both. They'll be a little bit rounded like the s, but they'll still have lobes like the p. And when you overlap these 2 orbitals, you get this arrangement. You get 2 mixed orbitals, 2 hybrid orbitals. And look how far apart they can get, 180 degrees. So if you have sp hybridization, you have 2 sp orbitals that can form bonds, and they're going to get 180 degrees apart from each other. So if you have a linear molecule, you're going to have sp hybridization. The hybridization matches up with the shape. And again, here's our overlapping orbitals. The sp hybrid overlaps with the 2p from the fluorine, here and here. Now our next example will be boron. He has 1 more electron than beryllium. So he needs to hybridize 2 p orbitals instead of just 1 to make his hybrid. So these are called these are called sp2 hybridized orbitals. We're going to mix together the s and 2 of the p's, and we get these 3 guys, overlap them together, and look, we have a trigonal planar arrangement. Again, the hybridization matches up with the shape. If you have sp2 hybridization, you're going to get a trigonal planar shape. carbon, sorry, does sp3 hybridization. He has one more electron than boron. So he's going to hybridize his S and all three of his P's to make sp3 hybridization. And that gives you 4 hybrids. We start with 4 orbitals and we get 4 hybrids when we're done. We haven't changed the number of orbitals, we only changed their shape. And now I've got 1 electron in each orbital. They're all open for business. They can all make a bond. Your bond angles are 109.5. I'm tetrahedral. So if you have a tetrahedral shape for your electron groups, you have sp3 hybridization. Sorry, water. Let's take a look at water. He has oxygen has oxygen has 4 electron groups. So his hybridization is sp3. 2 of these sp3 orbitals are available for bonding. 2 sp3 orbitals contain lone pair electrons. Our electron group geometry is tetrahedral. My molecular geometry is bent or angular. Okay. So in summary, if you want to figure out your hybridization, step 1, draw the Lewis structure. Step 2, figure out the electron domain geometry. That geometry gives you your hybridization. If you have 2 electron groups, your sp. 3 electron groups, you have sp2. 4 electron groups, sp3. So again, here's another summary. If I'm linear, I have sp hybrids, and I have a 180-degree bond angle. If I'm trigonal-planar, I have 3 sp3 hybrids. My examples are BF3 and SO3. If I'm tetrahedral, I have 4 sp3 hybrids. Examples: methane, ammonia, water, the ammonium ion. They all have this shape for their electron groups. Okay, onward. Well, this is great, but what about double bonds? What about triple bonds? How do we handle that? Well, what happens is that if a compound wants to make a double or triple bond, it will leave one of the p orbitals alone and not hybridize it. And that p orbital will be available for a double or triple bond. Now, there's 2 kinds of bonds that can happen. A sigma bond, which is head-on overlap, and pi bonds, which are sideways overlap. And you get sideways overlap with those p orbitals that have not been hybridized. Oh, sorry. So here's my example of a sigma bond with head-on overlap. Here's my overlap right here. These guys are pointing directly at each other. This is a sigma bond. All single bonds are sigma bonds. The electron density is between the nuclei. For pi bonds, we're going to get sideways overlap of p orbitals that have not been hybridized. So with these pi bonds, the electron density is above and below the nuclei rather than in the middle. So here's your sigma bond, here's your pi bond. You get the pi bond with that sideways overlap of the p orbitals when you have double and triple bonds. So here's an example of how this looks like in various molecules. Here I have acetylene. I've got 2 carbons. I'm only going to hybridize one of the p. So I'm going to have sp. And I'm going to leave the other p's alone so they can make a double and a triple bond. So the first bond is a sigma bond, and the second and third bonds are pi bonds with sideways overlap here and here. So now we're going to go into breaking the octet rule and what's going on with the hybridization for these guys. Well, what's going on here is that when we do the hybridization, when we're mixing orbitals, again, it's like knocking down walls in a house. We're going to hybridize an S, all 3p, and then we're going to grab one of those D's that are not being used. We're going to hybridize all these guys. We're going to hybridize 5 orbitals to get 5 hybrids. And these 3D orbitals, we're not going to hybridize them. We're going to leave them alone. We don't need them. We're going to use our hybrids. These are sp3d hybrids. I got 5 of them, 5 locations to make a bond. And this is why I can break the octet rule. I'm going to hybridize the d orbital, and that'll give me an additional location to make a bond. So if I have trigonal bipyramidal shape for my electron group geometry, that means my hybridization is sp3d. Here's an example of that. Arsenic pentafluoride. So I've got my bonding scheme here for this molecule. My hybridization on the arsenic is sp3d. I've hybridized 5 atomic orbitals to make 5 hybrids. 1, 2, 3, 4, 5. And so that means I can bond with 5 fluorines. And that's what that looks like. So my hybridization scheme is sp3d on the arsenic and a p on the fluorine. All the hybridization happens on the central atom. Okay, no hybridization on the F, it's just the P. Okay, here's our Lewis structure. Gives us the connections, but it's not giving us the shape. Here's my shape, trigonal bipyramidal. Okay. Next, we have 6 electron groups. That means we need 6 places to make bonds. So we need to hybridize 6 atomic orbitals to make 6 hybrids. So I'm going to grab an S, 3p, and now I'm going to take 2 of the D. I'm going to mix these all together for a total of 6 hybrids. I got 6 sp3d2 hybrid orbitals. Now I've got 6 locations where I can throw an electron in there and they're open for business. They can make a bond. You can also use d orbitals to make pi bonds, but that's outside the scope of this class. All right, here's an example of sp3d2 hybridization, SF6. Sulfur hexafluoride. Very stable, very inert, very unreactive, very happy, just like this. Here's our Lewis structure. I got 6 fluorines on sulfur. I'm breaking the octet rule. So here's my bonding scheme. I've got sp3d2 hybridization on the sulfur, and he's going to do valence bond overlap with the p from your F atom, because those valence electrons on F are hanging out in the p atomic orbital. So there's your bonding scheme. We go more into bonding schemes in the companion lecture to this, where I go over the examples from the textbook. All right, so here's a summary of what we talked about. If you have 2 electron groups, you're linear. Your hybridization scheme is sp, and you look like that. 3 electron groups, trigonal planar, sp2, hybridization. 4 electron groups, tetrahedral, sp3. 5 electron groups, trigonal bipyramidal, sp3d. 6 electron groups, octahedral, sp3d2. And here's all our bondings. Okay, again, I'll run through examples of this in the other video. All right, onward. So what's going on with resonance structures? We talked about that in chapter 10, where we have 2 equally dominant Lewis structures. And so that double bond, that multiple bond, moves around. Remember, the connections don't change, only the location of the double bond. If you don't have resonance, you have what's called localized electrons. They're kind of trapped between 2 atoms. But if you have resonance, those electrons are shared by multiple atoms, and they're called delocalized electrons. If you have resonance, like I said in chapter 10, extra stability when you have resonance. Okay? So here's an example of a molecule with resonance, benzene. Remember, benzene is a 6-membered carbon ring with alternating single and double bonds. So he's got pi orbitals that he did not hybridize. He's leaving them alone so they can do a sideways overlap. And that's what they look like. Here's my pi bonds with sideways overlap. But I can do this, or I can do that. I have resonance. So what I really have is this. You have electrons smeared around the entire ring. That's called delocalized electrons. This gives benzene extra stability. All right, I'm going to stop here. And I used a different recording software this time, so I have good confidence that this worked properly. And you guys will actually see all the PowerPoints, and it'll match my voice and what I'm saying. Yay! If you have any questions, put a comment below the video in YouTube, or just shoot me an email. Shooting me an email is faster, but I'll still respond to all the questions. All right, so that's it for me. So I'm going to get out of slideshow. Come on. Go back to my recording software and hit stop.